Hello there. In this video we're going to discuss another measure of variation or dispersion for a dataset known as the average absolute difference, or sometimes called the mean absolute difference. So as we should already know, the standard deviation for a dataset with x values can be calculated by taking the square root of the sum of the square differences between the x values and the sample mean divided by the sample size minus 1. So pretty much this measure of dispersion tells you on average how things vary with respect to the mean, which is pretty much this interior portion. Of course, if we have a symmetric data set for which we have some values on the left and the right of the mean, the difference between them will be equal but opposite signs, so we square that value so they don't cancel out when we sum those values. But why can't we just take the absolute value of those differences and sum up those absolute values? Because that pretty much will demonstrate the same exact idea as what this standard deviation does, right? And then we don't have to do the square root and the square value, and possibly even divide by n instead of n minus 1. So in this video, we're going to address these questions and also discuss the effect of replacing the mean with the median and how that affects the representation of the dispersion. Alright, so let us introduce this new measure of variation that we're going to be working with, and I'm going to be denoting this as capital M, so short for mean absolute difference. So this is going to be equal to the sum of the absolute value of xk minus x bar, all divided by the sample size n. So as I had already mentioned before, you may want to replace x bar with the median. And why do we want to possibly do that? Well, remember, if we introduce an outlier to a set, the median probably will change less than that compared to the mean value, right? So that's one of the reasons. So the median is a little bit more resistant to outliers, so we probably want to measure a dispersion that has the same exact effect. So let's begin this analysis of the comparison between these two and the effects of outliers, or without outliers, by considering this data set S, which is going to consist of the numbers 3, 4, 7, 7, and 9. So I leave to you to verify that the mean of this particular data set is going to be equal to 6, and the median of this particular data set, which I'm going to abbreviate as MED of S, is going to be equal to 7. So if you calculate the standard deviation of X with respect to, so I'm calling these values in the set S or X. So if we calculate the standard deviation while still using the value of x bar in that measure of central tendency, so that's of course going to be equal to the square root of the sum of xk minus x bar, the quantity squared, all divided by n minus 1, you can find that this value actually comes out to approximately equal to 2.45. So instead of using the mean, what about the median? So there isn't really no presence of outliers here, so the probably standard deviation probably won't change that much, right? But we do see that the mean is 6 and the median is 7, so they definitely will give us some different answers, right? And you may want to discuss or, talk to yourself, about is that difference significant or not. So if we calculate this with respect to the median, so I'm denoting these things with subscripts to the left-hand side, right? So this is going to be equal to the square root of the sum of xk minus the median of S squared, all divided by n minus 1. And you can find that this is going to be approximately equal to, 2.69, right? So these two are relatively close, mainly. I mean, that is a subjective criteria. But as we mentioned before, if we look at this set, subjectively there are no outliers. So if there is no outliers, then these values should be approximately similar, because the mean and the median should also be approximately similar, right? But of course that is related to the skewness of the data set, right? So it's possible that if your data is skewed, you may want to use the median over the mean also, for the same exact reason. And of course we see that the difference between these two, which I'm going to represent by delta, is only 0.24. So now let us do the same exact calculations for the mean absolute difference with respect to the mean and also the median. Okay, so let's calculate the mean absolute difference with respect to x bar. So what is that? So that's going to be equal to the sum of the absolute value of xk minus x bar, all divided by m. And the mean absolute difference with respect to the median of the data set is going to be calculated by doing the sum of the difference between xk minus the median of s, all divided by m. You can find that the first value is going to be equal to 2, and the second value is going to be equal to 1.8. Yes, these numbers are different than the standard deviation because it's different ways of representing the same exact thing, right? So you interpret them this a little bit differently because yes, the mean absolute difference and the standard deviation are both going to be in the same exact units as your data value measurements, but their magnitudes will represent different things, right? So just keep that in mind. So yes, 2.45 is bigger than 2, but that doesn't really mean anything because they represent different measurement styles. Okay. So again, it's the same exact set, so we can have the same exact consequences. So there are no outliers. Therefore, these values should be approximately similar, right? And we see that there is a difference between these of about 0.2. So a difference of 0.24 with the standard deviations is pretty much equivalent to a difference of 0.2 with respect to the mean absolute difference for this particular data set. So now what I want to do is I want to talk about another set, T, and T is going to consist of the numbers 3, 4, 7, 7, 9, and 30, which is just the same thing as saying the original set S unioned with the number 30, right? So yes, this number, more so subjectively, is going to be really different than the others, right? So this is our outlier that has been introduced to S. So now we can compare the mean of T, the median of T, the standard deviations, and the mean absolute differences of S versus T. So the first thing that we want to do in this analysis is to calculate the mean and the median of this particular set T, right? So our new mean, right? So I'm just going to call it x bar. You can denote it in another way like x bar star or x bar t or anything, but just make sure if you're comparing them and you're listing them next to each other, make sure to call them different things. Else you have two different x bars floating around and that's a little ambiguous when you start communicating those things. So you can find that the mean for this data set to be equal to 10, and the median for this particular set T is going to be equal to 7. Right, so these are the new values, and these are the old values. So let's bring them back and sort of compare. So the old mean was 6, and the old median was 7. So notice that the median didn't change. Well, it sort of changed, but not really, because we have these two middle 7s. So it's not necessarily the same 7, it's just the next 7 in sequence, right? So the median didn't change that much. And compared to the mean, it definitely changed significantly more than that of the median. But that shouldn't be a surprise to you because we already declared in our discussion on measures of central tendency that medians are more resistant to outlier introduction, right? So let us see the effect that they have on the actual measures of dispersion, in particular the standard deviation and the mean absolute difference, okay? So let's bring those values back. So if we look at our our standard deviation for x based on the mean, we can find that's approximately equal to 10.04, and the standard deviation of x based on the median is going to be approximately equal to 10.56. So again, we have some difference there, in particular 0.52. And if we look at our mean absolute difference with respect to x bar for this new set T, so all these calculations are for set T, okay? So the mean absolute difference with respect to x bar is going to be equal to 6.67 approximately, and the mean absolute difference with respect to the median is going to be approximately equal to 5.33, with a difference approximately equal to 1.33. right? So definitely there is a larger magnitude difference here because yes, the range for this particular set is going to be a little bit larger. Then of course the measures of dispersion will change a little bit more. Therefore, there will be a more significant difference between measures of dispersion based on the mean and the median, right? Because we see that there is a difference between these values. Therefore, we should see a more significant difference in the measures of dispersion if we sort of keep everything fixed and change these particular values. So now what I want to do is I want to compare these measures of dispersion with the old measures of dispersion with the sets that did not have the particular outlier, right? So like a before and after, like an S versus T, right? Because here we're just comparing the values of T with respect to standard deviation and mean absolute difference. But we should be comparing these measures of dispersion with and without the outliers as well, so that it's a very balanced set or fair analysis. So let's look at our standard deviation based on the mean, right? So if we look at the set S, we obtain a standard deviation of 2.45. And for set T, we obtained a standard deviation of 10.04. And we obtained a difference of 7.59. And if we look at our standard deviation based on our median, so first, for set S, we got a standard deviation based on the median of 2.69, and then we obtained a new standard deviation 10.56 based on our median associated with the outlier T. And let's change colors. Let's keep it the same color scheme. And we see that's going to be a difference of approximately 7.87, right? So these numbers here is what happens when an outlier is introduced, right? Therefore, we do see some difference between these measures of dispersion before and after a outlier is introduced. So let's see if the mean absolute difference has a similar, less, or more extreme difference before and after these values are introduced, right? So similarly, we have our mean absolute difference for x bar. We have our mean absolute difference for the median. We're going to compare the values of no outlier versus outlier, so that's a fair comparison. And let's see what happened here, right? So we first start off with 2 and 1.8. And then 2 changed into 6.67, and 1.8 changed into 5.33. So let's look at the differences between these values. So we got 4.67 for the first, and 3.53 for that. So yes, since the range did change, both of these measures of the dispersion did increase, because yes, the set became wider and more spread out. But notice that these values did not increase as much. Did not increase as much as the standard deviation values. Yes, they do measure slightly different things, but they are in the same exact unit, right? And usually we use these calculations to do other things. For example, calculating the line of best fit or the least squares regression line. Right? So you may be asking, okay, so what and why do I care and what can I come away with this, right? So let's assume we have some, fairly correlated data, and we have a line of best fit. So we introduce an outlier. So outlier is going to be, let's say, somewhere down here, right? So our new line of best fit normally is going to be this, right? So when we start to forecast this error, right? Because if this truly is an outlier, so our data is going to go here. This forecast model is going to go out here, and this difference, right? This difference, or error, rather, magnifies. Because the error is actually the difference between the line of best fit Well, that's the residual. The error is the difference between the predicted value and the actual value that we are trying to estimate, right? But in either case, the error is definitely going to magnify because the true values should be located around this linear regression line if this linear regression line matches all the appropriate criteria for us to use it. For example, the data should be linearly correlated up to some degree. But the error is going to magnify extremely if you use a wrong regression line. So instead, you can base that linear regression line on something that is more resistant to outliers, right? Or less sensitive to outliers, rather, right? So in that case, you may obtain, say, a linear regression line here, right? So it's not quite as good as the original line without the outliers. Yes, of course. But the difference in the error that's going to magnify is not going to be as extreme. Right, so that's one application of why you may want to use the absolute difference measure instead of the standard deviation. Now, in terms of the analytical perspective of why you may want to use it, so remember the variance, right? Actually, I'm just going to stick with the standard deviation here. So the standard deviation has this sum of xk minus x bar the quantity squared all over n minus 1. So let's assume for some reason we want to differentiate this object, right? Differentiate with respect to xk, right? If you know about derivatives. So we have eventually, we have this embedded here. So we're going to have to eventually take the derivative with respect to xk of xk minus x bar the quantity squared, and maybe evaluate that at xk is equal to x bar and see what happens there. I'm not going to talk about why you would want to do this or what you can use it for, but let us assume that you do want to do that. Right? So yes, this derivative does exist at this particular point because this is a parabola. This is a parabolic function with respect to xk, and it's shifted to the right x bar units, right? But if we take a look at, for example, the mean absolute difference, where we have the sum of the absolute value of xk minus x bar all over m, and we try and do derivatives of capital M, right, with respect to xk again, right? Eventually, we need to talk about, okay, what is the derivative of xk of the function xk minus x bar, say at the point xk equals to 2 x bar. And if you know anything about your basic functions from pre-calculus, then that we should know that the graph of that is going to be an absolute value function shifted to the right by x bar, assuming that this is the xk axis. And as we already know, this function is not differentiable at that point because it is a corner, right? Namely, the left-hand and right-hand derivatives are not equal, hence it's not differentiable there, right? So you can't take derivatives of the mean absolute difference, but you can take the difference of the standard deviation formula. So that is one advantage of the standard deviation, but it does come with that price that, you have a little bit more sensitivity to outliers, not as much resistance as you may have with, say, the mean absolute difference. Anyway, that's just an introduction to another measure of variation that you may want to use, and a little bit of discussion on outliers and how they sort of affect all these things and why we care. Hope you enjoyed. As always, if you enjoyed, please like this video, consider leaving a comment, and if you enjoy the channel content, please subscribe. We publish several new topics every single week. Thank you.